Okay. So these are the notes for section 4.1 in college algebra. So this section kind of revisits an old topic that we've seen already, which deals with linear functions and linear models. So what we know from, what we know about linear functions is that they have a constant rate of change, right? We know that linear functions have a constant rate of change as they are measured by their slope, right? Y equals mx plus b. Right, that tells us about their linear equations. And if they're linear, they have a constant rate of change. Which is measured by their slope. So this value right here in a linear equation is it's a constant rate of change measured by slope. In other words, the slope could be written as the change in y over the change in x. So how do we know if something is linear or not? So if we have a table full of raw data like we do here, so this is a measure of the number of grams of E. coli bacteria after X amount of hours. All right. So I want to determine if the following data set has a linear relationship and explain why or why not. So what you're really doing is you're trying to see if the slope exists between each data point. All right. So if I go from here to here, right, if I go from the first data point to the second data point, if I calculate the slope between these two data values, I'm going to get a value, right? Well, that value better be the same as the slope between these two data points and then the next two, and so on. If I get the same slope for each individual data point, then I will have a linear relationship. That means it'll have a constant rate of change. So in order to determine if something is linear or not, to determine if a data set is linear, calculate the slope for all the raw data. So you get one of two possibilities. I know this seems tedious, but that's how you would check it. If the slope is the same, for each data point, then it's linear. If the slope m changes, for each data point, then it's nonlinear. So I think this will be more intuitive when you see it in action, but let me calculate the slope. Between the first data point and the second one. So this is x1, y1, next to y2. So you know how to calculate the slope. It's y2 minus y1 over x2 minus x1. So that's going to be 0.12 minus 0.09 all over 1 minus 0. So when you do that, use your calculator for it. So 0.12 minus 0.09 gives me 0.03 over 1, which is obviously 0.03. Alright, so now let me do this again between. So now I'm going to do it for the next set of data. So this will be my next point, and this will be my next point. So the slope here is 0.03. In order for this to be linear, this needs to be 0.03 between each data point. That would mean I have a constant rate of change, which means I would have a linear data set. So let me look at the slope between 1 and 0.12 and 2.16. All right, so 0.16 minus 0.12 over 2 minus 1. So 0.16 minus 0.12 gives me 0.04 over 1. Uh-oh. What does that mean? That means that the slope between these two order pairs is 0.04. So guess what? The slope is changing between each data point. So this is actually nonlinear. Since the slope is changing in value between the data points, the data is non-linear. Okay? Now, I only had to see one example of where it was not 0.03. But if this were 0.03 and the next two were 0.03 and so on, then it would be a linear data set because it would be constant. But because it's not constant, these values are not constant, it means the data is nonlinear. So that's how you check to see if data is linear or not. It's pretty straightforward. And this page is pretty easy. This is almost like a rehash of what we did in chapter 2, I believe. So determining whether a linear function is increasing or decreasing. Well, that just deals with the value of m. So if I have a linear function and m is positive, that means it's increasing. And it's decreasing if the slope is negative. Or it's constant if the slope is 0. So, yeah, these examples should be relatively easy. So these linear functions right here, well, my slope here is 5. Obviously that's positive. So that means f of x is increasing from left to right. No problem there. My slope here is -2, which is definitely negative, which means g of x is decreasing from left to right. Now, in this function right here, there is no slope. I just have a y-intercept. So my slope here is 0, which means h of x is constant or horizontal from left to right. So yeah, that example should not be challenging to you. I mean, linear equations, linear functions should be a pretty common topic for you at this point in the course. You've seen them enough to know that, you know, their slope and y-intercept and what they represent, what they mean, stuff like that. Now, what we might be more interested in this section is building linear models from verbal descriptions. So, in a word problem, if you see a description that says something per something, like, for example, dollars per hour, or miles per hour, or feet per second, anything like that. If you see anything being described with these kinds of units, that means it's usually talking about the rate of change between two variables. In other words, it's probably dealing with a constant rate of change. Which means it's dealing with slope. And if it has a constant rate of change, then it's linear. So, if in a word problem you see something like dollars per hour, miles per hour, or something like that, then it's probably talking about a rate of change. So this example, a company has just purchased a new machine for its manufacturing facility for $120,000. The company decides that the machine depreciates by $12,000 per year. So I want to find a linear function that expresses the value of the machine as a function of its age, x. Okay, so I'm building a function. Specifically, I'm building a linear function. So I have an independent and dependent variable. My independent variable is x, which is the age of the machine. And my dependent variable is, using function notation, is v of x, which is the value of the machine. So I want to build, since I have a linear function I'm trying to find something that looks like y equals mx plus b. But since I'm using v of x and not y, specifically what I'm looking for is v of x equals mx plus b. So if I could find the values of the slope and the y-intercept, I will have my linear function. So it's just a matter of finding those values in my problem. So if I could find the slope and the y-intercept, I'm good to go. So in the problem it says a company has just purchased a new machine. So a new machine, I'm going to highlight that, for its manufacturing facility for $120,000. The company decides that the machine depreciates by $12,000 per year. Now, just like I said on the previous page, if you see something with units that are like dollars per year, dollars per hour, something like that, then that's talking about a rate of change. So the dollars per year here, this value 12,000, that's in dollars per year. So that's a rate of change. So that value is describing the slope of this linear model. So because of those units, dollars per year, that's the relationship between the age and the value, dollars per year. So I know by that my slope is going to be 12,000. Now, is it going to be positive 12,000 or negative 12,000? Well, let's think about this. The value of the machine is depreciating. So if it depreciates, that implies it's decreasing. And what we know from a decreasing function, a linear function, means the slope is negative. So altogether my slope is negative 12,000. And my y-intercept, that's what b is. This is the value. So what does that mean in context of these variables? The y-intercept means I want to find v of x when the independent variable, which is age, is equal to 0. So let's think about what this means. This means I want to find the value of the machine when the machine is 0 years old. In other words, when the machine is brand new. So does our problem give us anything like that? Yes, it does. It says right here, a company purchased a new machine for $120,000. So when v is equal to, when x is equal to 0, my value function is equal to 120,000, which means this is my y-intercept. So that means b is equal to 120,000. So my linear function is v of x equals negative 12,000 x plus 120,000. That's my linear function. So, if I wanted to graph this on a coordinate system, obviously this is a decreasing line because I have a negative slope. So I don't have my ruler with me. Oh boy. So let me just improvise. So that would be my linear function. My y-intercept, that value right there would be, that's going to be 0, 120,000. All right. So what is the value of the machine after 4 years? Well, that means I just want to find the value when x equals 4. So you just plug it into your value function. So you're going to get negative 12,000 times 4 plus 120,000. And then calculator time. Plus 120,000 gives me 72,000. So what is the value of the machine after 4 years? $72,000. Well, this is redundant, huh? Let me make an edit here. Let me say, when will my machine have a value of $108,000? So this means, so when will the machine, that means I want to find x when the value is 108,000. So I'm going to set my equation equal to 108,000 and solve for x. Subtract 120,000. We get what? Negative 12,000x equals, so 108,000 minus 120,000 gives me negative 12,000. And you divide by negative 12,000, you get x equals 1. Which means, when will the machine have a value of 108,000? After 1 year. That's it. Yeah, we're pretty short section. So, you know, properties of linear functions and linear models. Really not much to it. Modeling is something you're going to see a lot in Chapter 4. This was dealing with linear modeling from descriptions. And in the next section in 4.2, we're going to look at building linear models from data and doing things we call regression. But that's the end of this section.